This is the screencast for section 2.1, example 3. The definition of a limit. Well, you've worked with limits in pre-calc, but those dealt with x approaching infinity or y approaching infinity. Now we're going to look at some limits that neither x nor y are approaching infinity, but more of a limit in the middle of a function. Now mathematicians are getting away, actually teachers are getting away from explaining the epsilon delta version of a limit, but I don't want to deprive you of that experience, so here we go. We're going to say that f is defined in a neighborhood of c, and let c and l be real numbers. So we've got this c value here and our l value here, so c is an x value, l is a y value. The function f has a limit l as x approaches c, so as our x values that we plug in get really close to c, the y values hone in on this l value. Given any positive number epsilon, okay, so epsilon will be here. This is our little window of y values. There is a positive number delta, our little window of x values, such that for all x, okay, here we go. Delta is bigger than the difference between any x value and c value we plug in, which is greater than 0, which is why they have absolute value around there. So in other words, the smaller and smaller and smaller we make delta, this window around our specific x value we're trying to find the limit at, c, the smaller and smaller we make that, as long as we take the difference in those x values, then our y values, the difference in our little y values here, are going to be smaller than our epsilon, which is the window around L, the limit. So if our window around C gets smaller, that implies that our window around L gets smaller. That means the limit as our x values approach, specifically C on the x-axis, our y values are going to approach L on the y-axis. Now be careful, because this doesn't mean that your y values have to equal L. They just have to approach L. Their limit has to be L. So here's some examples on the right here. If we look at this function, which is x squared minus 1 over x minus 1, which you know from pre-calc that has a removable discontinuity at x equals plus 1, so here it is. Specifically a removable discontinuity at 1, 2. The limit of f of x as x approaches 1 is going to be 2. However, f of 1, so the function's actual value at 1, is undefined. There is no actual value there. The function approaches 2, but doesn't actually get there. It has a limit of 2. Now b, we've made a piecewise function so that at x equals 1, the function is defined. However, that doesn't change the limit. The function is still approaching the y value 2 as x approaches 1. But the function's value at 1 is in fact 1. We've now defined it. It's not undefined anymore. We've defined it to be 1. Then this last one, we've actually just simplified x squared minus 1 over x minus 1 to be x plus 1. So this is a line. The limit of f of x as x approaches 1 is 2, and f's value at 1 is also 2. This is a continuous function. Now there's a lot of information on the next page in your notes, and you're going to have to take some time and look through this yourself before we go on to the example. But basically, you've got some rules with properties of limits, and they may seem self-explanatory, but the best way to remember these rules is to ask yourself why. Why can I split the limit of a sum of two different functions and just add their limits together? Why, if I have the difference of two functions and their limit as x approaches c, can I just subtract their limits? Why can I just multiply the two limits together? Why can I just take a constant times the limit of a function? Why can I just divide the two limits of two functions? And why can I just raise the limit to a rational exponent? Another one over here on the right is that if the limit of a k, a constant function like y equals k, as x approaches any value ever, will just be k. The y value is always the same. And the limit of the identity function, so the limit as x approaches c of x, is in fact just c. X equals y, so if x equals c, y also equals c, so that's going to be your limit. And a limit that you have to memorize for right now, we are going to discuss why this is later, but for right now you are going to have to memorize it, is that the limit as x approaches 0 of the sine of x over x is 1. And I included a little picture there so you can kind of see visually why its limit is 1. As x approaches 0, the y values are getting closer to 1. So finally, here we are, example 3, using properties of limits. So we're going to use the observations, the limit as x approaches c of k equals k, and the limit as x approaches c of x equals c, and the properties of limits to find the following limits. Okay, I know that you may be thinking ahead, but as I've told you before, it is so important to show your work in this course. So please show every single step in your in working with limits on your homework and practice. So for part A, I'm going to look at the limit as x approaches c of 3 different functions being added and subtracted. Well, I've got a property that says that I can split those. Now on this first term, I've got a property that says I can take the limit as x approaches c of just x and then cube it. On the second term, I'm going to use that same property, but first I have another one that says I can take a coefficient and put that outside of the limit. So I have 4 times the limit as x approaches c of x, and then I'm going to square that. And the last one, I have a constant function, so the limit as x approaches c of 3, I already know is just going to be 3. So now one last step. The limit as x approaches c of x is in fact c, and then I cube it, plus the limit as x approaches c of x is c, so then I have the 4 in front and I'm squaring the c value, minus 3. So this is the answer, but it was important that you show your work and only use the basic limit properties that were shown in the instructions. Part B. First I'm going to split the limit of the top function over the limit of the bottom function. And now I'm going to break apart each term and its exponent. And now finally I can use that the limit of x approaches c of x is just c and simplify my answer. C to the 4th plus c squared minus, well this is the limit as x approaches c of a constant, so that's just the constant, all over. This will be x squared and then plus my constant of 5. Oops, c squared plus 5. So now try problem number 5. I'm going to dive right in. I'm going to split each term that I'm adding and subtracting into its own individual limit. And now I'm going to put the coefficients out front and then leave the exponents outside of the limit. This third term, I know that the limit as x approaches c of x is just c. And then the last one, I know that the limit of a constant is its constant. And now I can simplify 2c cubed minus 3c squared plus c minus 1. Then now try problem example 6. I'm going to split the limit in the numerator and the denominator. And now separate each limit with its exponent on the outside. And after I simplify, as you may have guessed, I get c to the 4th minus c cubed plus 1 all over c squared plus 9.